Questions about anything last time? I put some practice stuff for the midterm next Wednesday that's in class on the home page. So I'll review that kind of stuff on Monday. So this will give you a chance to look at it before then. I wanted to talk about, kind of review the concept of a good kernel and some of the most famous best kernels that come up in the subject. Let's see, there was a fact that Stein did quite early in the book, much earlier than I would have done it. And one reason he did it early is he wanted to demonstrate the usefulness of the good kernel idea. And I'll explain that later on in this lecture. Let's see, the fact is, if f is piecewise continuous on minus pi pi, and all its Fourier coefficients are 0, then the function is basically the zero function. F of x naught has to be 0 at all points x naught where f is continuous. And I'll talk about Stein's interesting proof in the book, but first I'll give you my proof. My proof, we worked hard to get Parseval's theorem. Parseval's identity. Okay, we know Parseval's identity holds for piecewise continuous functions. So Parseval's identity would tell me that the summation, let's see, what's this, 1 over pi summation, as n goes from minus infinity to plus infinity of those Fourier coefficients. Those are the CNs, by the way. That's the complex, that's Stein's notation for the CN complex Fourier coefficients. What is the formula? The sum of those coefficients squared is 1 over pi times the integral from minus pi to pi of f of x squared dx. Well, if all those Fourier coefficients are 0, this holds when f is piecewise continuous. So it can have jumps, but otherwise it's continuous. Finitely many jumps. Okay, if all of these are equal to 0, if all those coefficients are 0, then this sum would be 0. And if that would mean the integral has to be 0. But think about a continuous spot where f is positive. At a continuous spot where f is positive, there would be so let's say we would have an x, let's say where f, the absolute value of f squared is positive. So if x naught is here, and f of x, let's call this f of x naught squared. If that's not 0, then that would be a strictly positive thing. And at a continuous point, let's let epsilon be equal to f of x naught squared over 2. Then by the definition of continuity, I could get a delta here so that let's see, this would be a x naught minus delta and x naught plus delta. And if I take half that thing, so let's see. Yeah, this is my epsilon right here, which is half that. If f of x minus f of x naught, absolute value squared, is less than that epsilon, that means it would be above this dotted line. Dot, dot, dot. And so the graph of this function f of x, this be the graph of f of x squared. And so you see that graph would be above this rectangle here. And so this rectangle would be underneath, and that would show that the integral, we see that the integral from minus pi to pi of f of x squared dx would be greater than the area of that rectangle. And that area of that rectangle would be 2 delta times epsilon. Of course, that's greater than 0, and that's a contradiction. That sum on the left side we're assuming is equal to 0. So it means f is a pretty stupid function. A piecewise continuous function would have to look like this. I mean, a piecewise continuous function that's 0 wherever it's continuous would look like there'd be finitely many spots. Here's minus pi. Here's plus pi. There'd be finitely many spots where the function maybe isn't 0. Maybe not 0 there, maybe not 0 there, maybe not 0 there. But otherwise, it's always 0. At any spot where it's continuous, it has to be 0. Questions about that? Okay. Well, I want to show you the famous, some of the famous kernel ideas that Stein is going to use to demonstrate this in his own way. And a classic kernel from history is, so maybe this is the most famous good kernel I'm about to show. Most famous good kernel. I'll cook it up for you. It's the famous Gaussian distribution. So let's see. It looks like a bump. It goes to 0 really fast at infinity, and there's a bump like that. And we're going to want the area underneath this bump to be 1. And so the Gaussian is e to the minus x squared. That's the Gaussian distribution. And to make that area 1, we normalize it by dividing by 1 over the square root of pi. Okay, and to turn that into a good kernel, I want to concentrate that bump. Let's see. I want to concentrate that bump so it's gigantic at the origin and small everywhere else. So it's like pushing the bump toward the middle is what I'm going to do. Let's see, this is a good kernel. That means the integral from minus infinity to infinity of that phi of x dx is equal to 1. Okay, to make a good kernel out of it, I'm going to concentrate the bump at the, let's see, what's happening here? Let me make a bigger bump. Okay. So it's going to be 0 longer, but then the bump's going to be really concentrated like that. And the area under the bump is going to be 1. And a way to do that is to take your phi and call this phi sub epsilon. And let's see, to squish it, I would take phi of x over epsilon. That would squish that my original phi above. That would squish it down, but then the bump wouldn't get bigger that way. I need to make the bump get much bigger while I squish it. And that turns out to be exactly the right thing to do. Check that. You do a change of variables. So the change of variables. Let's see, you take u be x over epsilon, shows that the integral from minus infinity to infinity of phi epsilon of x dx is equal to the integral from minus u to minus infinity to u plus infinity of u, of phi of u du, and that's 1. That's a straightforward calculus exercise. I'll show you that famous calculation. This is why it's important. We'll use this calculation a couple times in the course. I want to show that the integral from minus infinity to infinity of e to the minus x squared dx is equal to square root of pi. Here's how you do it. It's kind of cool. I'll square that thing. And that's going to be pi, presumably. And let's see, a sneaky thing to do is to write that as, first I'll write it once with x as the variable. Then I'll write it again with a dummy variable of y. So that'd be e to the minus y squared dy. Then I realized, aha, this is what you would get if you did a double integral. Let's see. Oh, let's see. I'm going to, instead of going from minus infinity to infinity, I want to go from 0 to infinity. I'd realize in a second why that was going to be a problem. All right, think of Fubini's theorem. This is equal to a double integral from 0 to infinity, integral from 0 to infinity of e to the minus x squared times e to the minus y squared dx dy. Okay. If you would believe that if this were a big rectangle. But those functions go to 0 so fast that the outside part of the integral can be shown to be really small, and when you let the limits go to infinity. So that's a rectangle fact, and you can let the if that was 0 to r, and the other one was 0 to r, you could let the r go to infinity to get this fact. But when you look at it like this, you realize this is e to the minus radius squared. And then you realize, aha, this is an integral over the first quadrant in the xy plane, and the element of area in the polar coordinates is r dr d theta. And that's the first quadrant. And so in polar coordinates, this integral is equal to, let's see, the angle d theta is going to go from 0 to pi over 2, and the radius is going to go from 0 to infinity, and I'm going to get e to the minus r squared r dr d theta. So I'm going to move this r over in there, r dr, and then d theta. And this is the miracle that happens now. That's a simple integral. So this is going to be integral from 0 to pi over 2. Then I would do, let's see, that's what is that the derivative of? If I let u be equal to r squared, this would be 1/2. Let's see, this is u is minus, u is r squared. So du is 2r dr. And so when I look at this change variables, this would be an integral of 1/2 e to the minus, let's see, what is it? Minus 1/2 e to the minus u. Integrating between u equals 0 and u equals infinity. And then d theta. And what's that? That would be 0 minus a half. So I'd get the integral from 0 to pi over 2. One half. Oh yeah. That's e to the minus infinity would be 0, and e to the 0 is 1. So that'd be 0 minus a half. That's a half. And so that would be pi over 4. And now since the Gaussian distribution is an even function, so finally, the integral from minus infinity to infinity of e to the minus x squared dx would be the integral from 0 to infinity e to the times 2 times e to the minus x squared dx. Let's see, I'm going to square it. And that's, what is it? That's going to be 4 times pi over 4, which is pi. So check. When you to get that normalized, I need to divide it by square root of pi in the beginning. Anyway, Stein likes that calculation, and you'll find it in the book too. Okay. Now that I've got my phi sub epsilon, let me show you the famous use of phi sub epsilon. Let's see, when we were doing Fayer's, the Fayer kernel, so recall the Fayer kernel. Never remember where the accent goes. Fayer kernel. Remember, it had a bump, just like that, and we integrated from minus pi to pi of fn of t times f of x minus t is what it turned out to be, dt. I didn't define this didn't make a word for this back when I was doing it, but there is a word for this kind of thing. This is called a convolution of those two functions. Okay, and this was the Fayer kernel. So you convolve the Fayer kernel with a function. And this stuff was 2 pi periodic when we did it. If you want to do a convolution on R, the whole real line, I would write phi epsilon convolved with f, that's the symbol for convolution, at x. That stands for the integral from minus infinity to infinity of phi epsilon of t times f of x minus t dt. So that kind of, you multiply these functions together, you kind of jumble them together. One's going forward with respect to t and the other's going backwards with respect to t. So it's jumbling them all up when you calculate that product. That's something that comes up in practice, for example, in the Fayer kernel business, and the Dirichlet kernel business too. Exactly that integral showed up there. Okay, and here's an important fact that I'm not going to prove, but it's just elementary Fubini's theorem. A fact is that it doesn't matter what order you convolve in. Phi sub epsilon convolved with f is equal to f convolved with phi sub epsilon. That's an easy thing to check by change of variables. Okay, the feeling you should have about this kernel is that convolution with phi sub epsilon smooths stuff out. So the feeling is phi convolved with f smooths out f. Sometimes it's called a mollifier because of that. And approximates it. As epsilon goes to 0. And now I want to show you why. It's a good kernel argument. So let's calculate. So if I calculate phi sub epsilon convolved with f, that would be equal to minus the integral from minus infinity to infinity. And it doesn't matter what order I do it in. So I like this order here. F of t times phi sub epsilon of x minus t. And this is the value at x dt. And now if I think about making a difference quotient of that thing, so I would write a difference quotient. Let's see, a difference quotient would be phi sub epsilon convolved with f at x plus epsilon minus phi epsilon convolved with f at x, not x plus h rather, divided by h. And when you write that out, you realize, oh, I can put that difference quotient inside the integral. F of t would just sit there, and I would see that I would get phi sub epsilon of x plus h minus t minus phi sub epsilon of x minus t over h dt. And that function is so nice and dies away at infinity so fast, what you realize is that this integral nice, very nice, it's infinitely differentiable, and it dies away very fast at infinity. For big X, for big, dies away fast. In both directions. Which means that that integral is going to tend to, so we see that d by dx of phi epsilon convolved with f at x is equal to phi sub, it's equal to, I already did this once. It's the same thing. It doesn't matter what order you do it in. And when I did it in this order, I realized I could differentiate under the integral sign and see that this is the same as f convolved with d by dx. So I can, in other words, I can differentiate through that integral. And so even if f is not differentiable, this thing is differentiable because phi sub epsilon smooths it out. Okay, it doesn't matter what order you do it in. So the rule, we can differentiate through the convolution. To see that the convolution, we can do it again and again. To see that phi sub epsilon convolved with f is C infinity smooth, even if f is merely continuous. Okay. And see, that works. It works if f is continuous and bounded, for example. F is continuous and bounded. And if you really think hard about it, how wild you could let f get, you could see, or even if f is a exponential type, is piecewise continuous, if you ever studied the Laplace transform, you would have heard of exponential type before, and of exponential type meaning that f doesn't grow too fast at infinity. So meaning that f of x is less than or equal to some constant times e to the c absolute x on R. Okay. So let's see. I'll show you how this is used. So a theorem. C infinity smooth functions are dense. Among bounded continuous functions on R. And the y is going to be something that's very familiar. So if I were to take, for example, let's say I have a bounded continuous function, and I take phi epsilon convolved with f at x, and now I want to show that that's close to f. And you realize if you write those integrals out like we did before, let's see, this one I would write out as integral from minus infinity to infinity of phi epsilon of t times f of x minus t. And you realize, aha, I'm going to multiply by 1 here. Multiply by 1 in the form of the integral from minus infinity to infinity of phi epsilon of t dt. And when I do that, I would get here minus, I'd get the phi epsilon t here, and instead of f of x minus t, I get f of x. And I'm integrating with respect to t. And now you think, this looks familiar. This is the integral from minus infinity to infinity of phi epsilon of t times something that might be, that I'm thinking is small, at least near x. So that, in fact, that's small for small t. Because of continuity. And this thing is small for t big. So small outside. So let's say for t small, let's say for absolute t less than delta. And this is going to be small for absolute t bigger than delta. If epsilon is small enough. So that's the good kernel argument. You split your integral into two pieces. One where the good kernel is small, and one where the thing you're hitting it with is small. Let me show you the details about how it goes. Since f is bounded, we would have that f of x, f of t is less than or equal to m on R, since we're assuming it's a bounded continuous function. So I could write this, I'll write this integral as an integral from minus delta to delta. That would be phi epsilon t times, this is where this thing is small, and then I'd have the integral when t, absolute t is bigger than delta. I can make it bigger than or equal. Same thing. All right, and give me given epsilon bigger than 0, there exists a delta such that f of x minus t minus f of x is less than, let's make it epsilon over 2. If t is, when t is less than delta. Okay, so if I make these two integrals I1 and I2, forgot my dt here, then I1 is an easy one to deal with, because I would have absolute I1 would be less than or equal to, this good kernel is a positive thing, so I would get phi sub epsilon of t, and this absolute value of that other stuff this would be less than epsilon over 2. Okay, and this is exactly where the kernel phi sub epsilon is gigantic. But the good news is, even though it's gigantic on that small interval, the integral of the stupid thing is 1. So that's the key here. I can pull this epsilon out of the, this is going to be less than epsilon over 2 times the integral from minus delta to delta of phi sub epsilon t dt. And because it's a positive kernel, that would be less than the integral from minus infinity of phi epsilon of t dt. And that's equal to 1. So I get, because of that observation, I get that I1 is less than epsilon over 2. Now the I2, I could write as, let's see, that's going to be less than or equal to, this is going to be the integral over absolute t bigger than delta of phi epsilon t times this same old absolute value. And because it's bounded, this is bounded by 2m. And I claim that the integral as over t bigger than delta of phi epsilon of t dt goes to 0 as epsilon goes to 0. because the phi sub the bump is getting squished to the middle, and it's going to 0 really fast out there. Let's see, if I had to demonstrate that to you, here's how I would do it. This, because it's an even function, this is 2 times the integral from delta to infinity of phi sub epsilon of t dt. And that's equal to 2 times the integral from delta to infinity of, let's see, that'd be 1 over epsilon e to the minus t over epsilon squared. Then the key to estimating this integral is noticing that e to the minus t squared is is going to 0 faster than e to the minus t is. So let's see. Oops, that's weird. Uh-oh. Okay, let's see how I want epsilon to go to 0. So when epsilon is less than delta, then I would have e to the minus t squared over epsilon squared would be less than e to the minus t over epsilon for positive t. When t is bigger than delta. And this thing is simple to integrate. So you can calculate directly integral from delta to infinity e to the minus t over epsilon dt. And see that it goes to 0. So that's just a little technical calculus fact. You don't have to be able to calculate that integral to show it goes to 0. Let me tell you what Stein does. Okay, so that's the end of it. So I've actually shown I can make I2 less than epsilon over 2 also. And what we see is that phi epsilon convolved with f tends to f. Okay, so, and this is a smooth function tending to a continuous function. C infinity smooth. And this f is merely continuous. Anyway, that's how it works. So if you tried to read Stein, he did a very similar thing. Reading Stein on page 40. He wants to cook up a bump function, like this good kernel, using a trig functions. So here's how he did it. It's kind of a neat trick. Let's see, I've got minus pi over 2 to plus pi over 2. The cosine function, here's 1. The cosine function looks like this. It's a peaks at 0. It's supposed to look symmetric. I missed. That's pi over 2. Okay. And here's what Stein did. So here's the function. Here's 1 here. He wants to make a bump function out of trig polynomials. So what he does, this blue function is cosine of x. This is the x direction. And he takes 1 plus epsilon cosine x. 1 plus epsilon cosine x. That would bulge this up a little bit. And notice that starting right here, it's above, that's going to be a minus delta and a plus delta. That's slightly above the line, the 1 line. And now he takes it to a gigantic power. So let's see. I need another color. Red. Oops, what's happening? Terrible's happening. Sorry. What color can I pick? How about turquoise? Okay, I take 1 plus epsilon cosine x and raise it to a gigantic power. Okay. That would make it get it really small here. And it's 1 at this red spot. And then it would get gigantic, because that's bigger than 1. And I'm taking gigantic powers. So here it gets small. And that's a bump function. And I want the area under that thing to be equal to 1. That's a bump. And I'm going to divide by a c to make the area 1. By a c to make the area under the graph 1. Okay, that's C. I'll put it here. That makes the area under that thing 1. Okay, so he made a trigonometric bump function that, and it gets a concentrated area at the origin. And the brilliant idea for doing this, so let's suppose f hat of n is equal to 0 for all n. Then that means that f is orthogonal to all trig polynomials. That means that f is orthogonal to Fair polynomials. Let's see, then f is orthogonal to all trig polynomials, including that big bump. The big bump. And that big bump is exactly like my good kernel. It spits out the value at a point where it's continuous. And this integral from minus pi to pi of f of x minus t times a big bump at I'm going to run out of time. F of t